All right, last time we had started section 5.1, addition and subtraction of integers. We'd taken a look at some addition models with integers, and we had just touched on kind of an in-between subject that we're going to cover a few of these things. The one we left off on was absolute value. We talked about the fact that absolute value is really a distance. That's actually why it's a positive quantity, is because we're calculating a distance. And then also, in spite of the fact that this definition looks like you're getting negative numbers, you're not. The part that's in the box says that the absolute value of x equals the opposite of x when x is negative. That's what it really says. The absolute value of x equals the opposite of x, which would then be positive because x itself is negative. So we're going to answer a few questions where we have to think about whether or not they're true or false. And then if they're false, to show an example of what makes them false or when they would be false. So the ones that we're looking at start out with the absolute value of x to the fourth is x to the fourth. So is that true or false?
True.
It is true. Any thoughts on why? It doesn't say that we have to explain, but any thoughts on why?
Because when it's inside the little bracket things, it stays positive. And so whenever you take away the brackets, it's just the same.
Okay, so let me clarify what you meant, I think, and you can tell me if I'm right. The x to the fourth that's inside of those absolute value symbols is already positive. Is that true? And so why is x to the fourth already positive?
Because an even number multiplied by even number is even, and an odd multiplied by even is even too.
Okay, so let me again change a little bit of the language you're using, but we have an even exponent, so we're multiplying a number an even number of times, right? So when I multiply a negative an even number of times, it will always become positive. Does that sound right? So x to the fourth is greater than 0 because we have x multiplied an even number of times. We'll say giving us a positive number. So since the since the x to the fourth is already positive, the absolute value simply doesn't change the value, right? It fits into the first description here. Absolute value of x is equal to x because x is already positive. Now, I didn't ask for an explanation, but I'm going to jot it down so that we can remember later. What happens on part B? True or false?
Sometimes true.
Sometimes true, which means it's sometimes false. Okay, so if it's sometimes false, we're going to count it as false, and we're going to show an example where it doesn't work. So it is sometimes false. So can you give me an example of a number where when I take it to a power of 5, and then I take its absolute value, it's not the same?
-1.
-1's a fabulous example. So -1 to the fifth and the -1 to the fifth like this are what we're comparing, the left side with the right side. On the first one, what is -1 to the fifth? Just that part of it. -1. Okay, so each of these are -1. But the first one, the left-hand side, is inside of absolute values, which then makes it a +1. So these two are not equal. And in fact, we could have chosen any negative value and it would have failed, right? It's the negative that's causing it to fail, not the fact that it's a 1. The 1 just makes it easy to work with. How about C? Absolute value of x is not negative. That is true. Distances, that's what absolute value is, are not negative. Cannot have a negative distance. How about the absolute value of x is positive? It's so tempting to say true. Okay, if it's false, there's got to be a reason why.
Because it's the opposite of the true one we just did.
So it's not quite the opposite. Can you see how it's not quite the opposite of number C?
Oh, no. It's false because
It could be negative. If x is already negative, then the absolute value would be negative.
But that still becomes positive.
It would be true. Because it's always, because distance doesn't.
There's something missing.
Not. I thought this.
Thanks, Emily. Okay, there's something missing from our description of the two types of numbers here. We've got two descriptions written down. One says negative.
X is less than 0?
Okay,
Is that what it
negative and positive. I'm missing something.
is?
0 is what I'm missing.
Oh.
All right, so can I do an absolute value and get 0? That's actually the issue. Because the difference between not negative and positive means not negative means that it can include 0, and positive doesn't. 0 is not a positive number, it's not a negative number. So over here, if you had the absolute value of 0, what would you get? 0. Okay? So have you ever looked, does anybody have one of the tracking apps on your phone? Like you can see where a friend or a parent or something is at any given time? We have Life 360, and my two girls and my husband and I are on there. And if you're in the same place, it will tell you the distance to get to that person or the time to get to that person is 0. Right? It will. It's 0. They're right there with you in the same house, probably in the other room, and you didn't know they came in, probably. So we do in fact have the ability to equal 0. So while an absolute value is not negative, and that's a true statement, it's not quite always positive. Most of the time it is, right? Usually the distance is somewhere far away. If I'm going to go and look for my husband on the Life 360 app, he's usually not inside the house with me. It's usually not what happens. But it could be the case that it is. So this is false, and it's false specifically when x is equal to 0. X equals 0 is also possible. And perhaps you hadn't really thought of it because in your mind you kind of categorize the number 0 inside of the positive numbers. It's not. It's not positive, but you might have thought about it that way. Okay, any questions on those? So if we were saying it the way that Elizabeth said before, we might have said it's mostly true, right? Or almost always true, but not quite always. All right, a few things about some properties before we move into our models for subtraction. We've got several properties showing up. Theorem 5.1 is the first one, properties of integers. We have seen pretty much these properties happen before, and they work very much the same way. We have the closure property. The closure property says that if we have two numbers that are integers and they're added, we get a unique integer. Right? We don't add integers together and somehow end up with a fraction or a radical. We don't. We end up with another integer. The commutative property of integers for addition says that we can add in either order. It's just like it was for whole numbers. The order doesn't make any difference. So -5 plus 2 is the same as 2 plus -5. Associative property, again, works the same way. A plus B plus C is equal to A plus B plus C. So the order stays the same, A, B, C on both sides, but the grouping is around different quantities. And the last one, the identity property of addition. What number can I add to things and they remain unchanged? 0 is the identity element. because a plus 0 equals 0 plus a, which is equal to a. Okay, so those are all the same. No new properties, really. We're just extending them to be able to be used with integers. The next two are actually, two theorems are actually slightly different. They talk about what happens because we now have negatives specifically. So we have the additive inverse property. We haven't had that before. The additive inverse property says that for every integer a, there exists a unique integer, the opposite of a, or negative a, such that a plus negative a, or negative a plus a, is equal to 0. Right? There's a polar opposite. In some sense, you can think about this saying that your number line is symmetric. If you can go 5 to the right, you can go 5 to the left. Right? There's a balancing. The 0 is the balancing point between the value and its inverse on the number line. And then we're going to talk in Theorem 5.3 about a few things that make things helpful. For example, negative of negative a, right? If you have integers a, b, and c, and you put two negatives, right, together, it becomes a positive value. And it might be easier to remind yourself that what this is really saying is that the first negative is thought of as the opposite of the negative a that's inside. Well, what's the opposite of negative a? Positive a. B talks about a property of equality. We saw this property of equality before. We just haven't seen it in reference to integers. If a is equal to b and we add c to a, then as long as we add c to b, they remain unchanged, right? So if two of my daughters right now are the same height, that won't last very long, but two of them are the same height, and if they both grow 1 more inch, they'll still be the same height, right? So if I add an inch to each of their heights, they remain the same height. This is the same thing. And on C, we actually get into a little bit of some of the things that Emily mentioned last time, seeing somebody talk about keep, change, and such like that, which we'll get more to in subtraction. But this talks about what happens when we add two negatives together. So if we add a negative A and a negative B, it's the same thing as flat out adding the A and the B and then making the result negative. So same signs, we keep the sign, right? So that would be what's going on there. We keep the sign that's negative. So now we're going to actually define subtraction, and I'll hand out the chips in a sec. So subtraction, integer subtraction says the following. For any integers a and b, a minus b is the unique integer, say n, such that a is equal to b plus n. And in a very real sense, we're actually saying if a minus b is equal to n, it must be true that we can add that b to the other side. So subtraction on the left moves to addition on the right, and I have an equality in terms of addition now, instead of in terms of subtraction. And Theorem 5.4, which is perfectly fine to mention and so forth, is not intended to make things more complicated, and unfortunately I do see teachers sometimes using this theorem to make it harder for their kids. They don't mean to, but it makes it harder for their kids than easier. So I remember having a teacher, and the teacher where I saw it happen the first time who really harped on this was in 7th grade, and she kept saying there's no such thing as subtraction. There's no such thing as subtraction. All there is adding negatives. And that's fine, and it's true, and it didn't mess things up in that particular class, but I have seen groups of students for whom that idea, namely what's happening in here, makes things a mess. In particular, it makes things a mess with things that could have been subtracted with whole numbers to start with, right? 5 minus 2. Okay, well, let's just think of it as subtraction. It's 3, right? There's no need, if it's 5 minus 2, to say, oh, but really, it's 5 plus negative 2. That can complicate things instead of being more helpful. So you have to be a little bit careful with the fact that properties need to be utilized in a way that are helpful, not complicated. All right, so I'm going to pause the video for just a second. I'm going to come and bring some chips out. So if you'll turn some desks together, just kind of where you're setting, groups of 2 or 3 or something like that are fine, and I'll bring over some chips. Okay, so everybody ready? All right, integer subtraction is a little bit messier than integer addition, even with the different models. So I'd like to show you a few things about integer subtraction that we will take a look with. Note in particular, as we're doing these different models, we're not trying to implore like number A. Our goal is not to change things from what they are, but to actually model why those properties work the way that they do. Okay? Why in the world is the opposite of negative A or negative A become positive? Right? So if y is a negative times a negative, a positive. So we can actually see that at play really nicely inside of our models. So if you will, what I'd like you to do is I'd like you to create some sort of piece of paper or spot on your desk that is your working board. And we're going to put 5 chips in that are, in this case, we did red, black, what did we do last time? Red and yellow. So we had red as our positive and yellow as our negative. Reminder to myself. So our red, was considered our negative chip, and our yellow is considered our positive chip. And I talked about the fact that it doesn't really matter what color they are, it's just what color these particular manipulatives are. So what you'll actually see usually used in our book is red and black. Black for positive, red for negative. And then you can use whatever colors you have. If you have pens or colored objects of some sort, just like sure you label for me which is which. Okay, so we're going to put in 5, oops, that was supposed to be a highlighter, 5 positive chips. So you're going to put 5 yellow chips into your circle. You were starting out with the images listed. So the image listed is 5 positives, and over here in the parentheses, 3 negatives. Okay, so we already have our 5 yellow. I need my 3 red. Okay, so I need 3 red inside my circle. Oh, I didn't say that right. I'm going to take it back. Let me erase them out. Give me a second how to say it right. Yeah, okay. We start with our 5 that are in our circle, and then we have to be able to remove 3 negatives. That's what that one is saying. This one means remove, very much the way that you guys like to do subtraction is take away. Okay? We want to remove 3 negatives, but I want you to notice is there are no negatives in my circle. That's what I wanted to say, right? There are no negatives in the circle. So in order to actually have a negative to remove from the circle, I have to insert one, but I can't change the value from the 5 that I've already started with. So what I do is I add them in 0 pairs. So I will add a red and a yellow in at the same time. The value of this circle is still the value 5. Okay? I still have 5 as a net value for this circle. And I can do this for each of the 3 negatives that I need to have present. So I now have a circle that still has 5 in my circle. This circle represents the quantity 5. Now I could add, infinitely many blacks and reds and yellows and whatever color I'm using. I could add them in as long as I'm putting them in both at a time. It starts out with nothing in it. I put in my 5, and I need to make sure that there are 3 reds to take away. I now have 3 reds to take away, so I'm going to remove the 3 reds because it says to, right? It says I'm supposed to remove my 3 negative pieces. And what I'm left with then is a circle that has how many and of what kind of chips? 8 positives.
That's kind of cool.
Okay, there's 8 positives. We did not use a negative times a negative is a positive in order to do that argument, right? I didn't do that. I didn't just insert 3 random yellow more pieces instead of taking away 3 red. I put them in 0 pairs, which then allowed me to take out the negatives that I was told to remove. And that's what the chip model would look like. The charged fields model, we saw this last time as well, looks very similar. It does all the same things, it just does them with positives and negatives instead of with chips. So I have 5 positives. And it says that I want to remove 3 negatives. Well, I don't have 3 negatives, so I put the positives and negatives in pairs. Once I have the 3 negatives in my diagram, I'm able to then remove them. And when I do that, the result of my circle the result of what's in my circle changes. Whoa, whoa, whoa. And I now have 8 positives in my circle. Sorry, I should have put equals 8 over here as well. 8 was the answer. I'm removing negatives. Now let's say that the problem started out and it already had negatives inside. Would I have to add them in 0 pairs? Well, maybe not, right? If the problem actually started out saying -3 minus -2 like this, in other words, I put -3 in, and it says to remove -2, well, I just remove the 2, right? So if they're already there, it's great, but when they're not, I get them in there by 0 pairing them up. Okay, the number line model is probably my favorite, okay? I'm going to draw the number line model. You're not going to like the drawing, but then I'm going to act it out, and they're going to be like, oh, okay. So let me draw it for you first. Still the same numbers, 5 minus -3. So from the drawing perspective, I start out at 0, and I come over here to 5. 1, 2, 3, 4, 5. So I'm at 5. Everybody good with that? All right, well, this says that I'm going -3. Well, if it were addition of 3, I'd go backwards 3, right? What we're going to do is we're going to actually go the opposite of that, and we'll move 3 to the right, right? This says that I should be going left, and this one says I want to do the opposite of what I would have done if it were addition, so I go to the right. And that's fine in general. But here's what I'd like for you to pretend, and I know our desks are all in a disarray, so pretend we have the nice array of desks in the room that we don't have right now. Imagine that this is 0, and I'm going to move 5 in that direction, okay? So I go 1 desk, and then I'm at 2 desks, I'm at 3 desks, I'm at 4 desks. I'm going to run out of space, but pretend I'm at 5 desks, okay? It says minus -3. What does it really mean? Well, the minus means I'm going to turn around. And the -3 means I'm going to go backwards 3 more. And where did I end up? At 8. So when you're thinking kinesthetically, you can actually use like movements to mirror what's happening. One of them talks about the direction you're going. Am I going forward? Am I going backward? And the other one talks about whether I'm turning around. So if I have a negative occurring in the middle, I turned around. Okay, and it would work the same way if I had a positive. So like, let's say that I had 5 minus 2 here, like really had 5 minus 2. So I would go forward my 5, wouldn't turn, you can do one of 2 things. You can either then just go backwards 2, right? Or you can turn around and go forwards 2, right? So if I go forward my 5, I can turn around and then I can go forward 2, however you define the negatives to be. So it works whether you have positives or negatives. Okay, our last one is our pattern model. We saw this one last time as well. Again, maybe not the go-to one for all of our kids, but there might be that one kid that this just hits right. And so it's good to have, an arsenal of things to use. So when we're working with the pattern model, typically what we want to do is we want to start with something that we know how to do with whole numbers already. For example, 5 minus 2, those are both whole numbers. We know 5 minus 2, it's 3. Our goal is to get this second number to become the -3 that my problem has in it. So I'm going to take this value and I'm going to go down 1. Well, 5 minus 1 is 4. And 5 minus 0 is 5. And by the time I have 3 of these, I should have established a pattern. My pattern is that I'm going down 1 every time in the subtraction piece, and the answer is increasing 1 every time. So if I go down 1 again from the 0, it's -1. And my pattern suggests that I went from 3 to 4 to 5, so now I'm at 6. So again, justification for why the opposite of a negative ends up adding the values together. And then the one we're looking for, I think two more, sorry. 5 minus negative 2, and it goes up 1 to 7. 5 minus negative 3 gives me the 8 we keep getting. Any questions? Okay, one last thing in this section. Order of operations. Have we seen PEMDAS before? Did you ever use, please excuse my dear Aunt Sally as a reminder for it? Maybe, maybe not. PEMDAS is actually not the best thing ever. It does definitely disguise a little bit of what's going on in the order in which it's actually written. We do, in fact, work in parentheses first. That's the P. And I mean within parentheses. So it's simplifying inside. Okay, it doesn't necessarily mean that you get rid of the parentheses, but you're simplifying what's inside of them. E is exponents. So we always do exponents second. What I want you to notice, the way that I've written it out, is the M and the D are side by side. There is not an order. Could very easily have called this PEDMOS and it would be right as well. It just doesn't sound as good. Right? Please excuse dear my Aunt Sally. That doesn't work very well. Okay, so what does this mean? Well, M is multiply and D is divide. But when we get to the point in a problem where we've eliminated parentheses, cleaned all that up, we've gotten our exponents taken care of, and we're multiplying and dividing, we are multiplying and dividing from left to right. It's all about moving from left to right with either of those operations occurring in whatever order they show up. And the same thing happens with the A and the S, the addition and the subtraction. So again, we're moving from left to right. I don't need to add before I subtract. All right, I can definitely subtract first if it comes earlier as I'm moving from left to right. So let's do an example of that next. So this does not have any parentheses, and it does not have any exponents, correct? So we don't have to deal with the first two steps of this ordering. We're down to the point where we're doing multiplication and division. And if I'm moving from left to right, what operation do you see that you will need to do first? The 6 divided by 2. So I'm going to rewrite the 5, the minus 2, and my addition. And what is 6 divided by 2? 3. And then I've got the dot 4. So after I've done the division, I can do the multiplication next. You don't necessarily have to write this in 2 separate steps, but if it helps you, go for it. Moving from left to right, still moving in the multiplication and division. I now have the 3 times the 4, which is 12. Okay? So no multiplication, no division left. So we're now on addition and subtraction. What are we going to do first?
5 minus 2.
Yeah, 5 minus 2 will happen first. Right? So 5 minus 2 would give me 3. And then the only step left is 3 plus 12, which will give me 15. All right, so here's what I'd like to do. I'd like to table the group work and for us to come back and do the group work next time, which means your homework won't be due on Friday. It'll be due on Monday. If you'd like to get started on it, that's fine. We will do the group work for 5-1 at the end of class. We will start 5-2, and then we'll just pause at about 15 minutes till the end, and we will start in on the group work then, okay? So homework, group work won't be due until Monday for 5.1.